Frequency modulation. What in the hell is frequency modulation? I don't know. Frequency modulation is used to transmit data in telecommunications and radio broadcasting and many other areas. In terms of synthesizers for music production, it's used to create complex sounds like the shot of a laser gun. Now in this video, I will explain how this actually works, and this includes the maths behind it, how to create and modulate those waveforms like sawtooth, triangle and square wave, and how to turn that into an actual sound. Don't worry if this doesn't mean anything to you, I will explain it in a short moment.
This is a waveform. It's a visual representation of sound, and it shows the amplitude of a signal over time, or in simple terms, it shows how strong the signal gets over time. For example, at the beginning, the signal is stronger than at the end. There are also some basic waveforms, which I will talk about now. Let's have a look at the waveforms and check how they sound. The first one is the sine wave. The second one is the triangle wave. The third one is the sawtooth wave. And the fourth one is the square wave. When we speak about frequency modulation, the frequency of one waveform, also called the carrier wave, will be controlled by a second waveform, which is called the modulating wave. The modulating wave describes how fast and in what kind of pattern the frequency of the carrier wave is changed. We have here three examples. My carrier wave is always a triangle wave. In the first example, my modulating wave is also a triangle wave. Now if we look at the waveform, we can see that the frequency fades continuously between two values. And that's also what we will hear. In the second example, my modulating wave is a sawtooth wave. And as we can see, the frequency fades continuously to a maximum value and then instantly starts at the minimum again. So it basically rises and instantly drops at a specific value. In the last example, the modulating wave is a square wave, and we can see that the frequency instantly changes between two values. Here we have the higher value, and here we have the lower one. Let's take a look at the maths, and we start again with the sine wave. Now this is a function, and for each x we put in, we get a value for y. If we do this often enough, we can create a wave with these values, like the sine wave. These values are also called samples. It's periodic, which means it repeats in intervals of 2 pi. In this case, our waveform has a frequency of 1, and we can increase the frequency. For example, here we have a frequency of 4, which will repeat in intervals of 2 pi. Now later, when we want to make this time dependent, if we want to have a frequency of 4 in 1 second, it would be easier to have an interval of 1. If we now set an additional variable, I will call it f for frequency, and we set f to 2 pi, then we get exactly that. To get the double frequency, we just enter 4 pi or 6 pi for 3 times the frequency, and so on. Now we can make it easier and just add 2 pi to our formula. And then we just can increase f. And for example, here we have a frequency of 5, and this waveform will repeat in intervals of 1. The other waveforms have no basic formula like sin x, which means we need to create them somehow. For this, and also to visualize frequency modulation, I've programmed a little tool in Python. You can download it from my GitHub page, the link is in the description. Now if you're doing some research how to create those waveforms like the sawtooth, the triangle and the square wave, you will most likely read about the Fourier series. With the Fourier series you can basically create any waveform by adding multiple sine waves together. I have here on the left my waveforms, which will be created with the Fourier series. And we can also see the formula for this. This is the formula for the triangle wave. This is the formula for the sawtooth wave. And this is the formula for the square wave. And if we choose the sawtooth wave, and at the beginning it's basically a sine wave, and if we increase the amount of sine waves which will be added together, then it slowly will become a sawtooth wave. Same for the square wave. And same for the triangle wave. The downside of this method is that if you want to use it for real-time applications, it's not really efficient. One other solution is to use the trigonometric functions on the right side. Now keep in mind there are many slightly different functions for those waveforms. There's not only one correct formula. And the simplest one is the square wave, because basically it's the formula for the sine wave here in the middle, and we add the sine function. The sine function turns any value which is greater than 0 to 1, and any value which is smaller than 0 to -1. And if a value is 0, it stays 0. And this way you get a perfect square wave. And if you want to amplify the square wave, then you just add an additional variable in front of it, A for amplitude. And if you want to shift it on the y-axis, then you add a constant and here. Now the formulas for the sawtooth and the triangle wave are a bit more complex, but the principle is basically the same. Here you have the sine wave, and you can see 2 pi times f times x, and here you set the frequency. Minus half p is just to shift this function on the x-axis, and that's it. And here you have the same. This time it's not sine, and it's 2 pi half f times x, and here you again set your frequency and you get your sawtooth wave. Let's do some basic frequency modulation, and we will continue with our sine function. We will modify it a bit. If we now add an additional variable, I call it m. If m is a constant, it will shift the function on the x-axis. Now, because we want to do frequency modulation, m is in our case not a constant, but a different function. And you can already see what happened. Now, m is our modulating wave, and this is our carrier wave. So Fc is the frequency of our carrier wave, Fm is the frequency of our modulating wave. And usually the frequency of our modulating wave is lower than the frequency of our carrier wave. And you can already see what happens. Now we are missing an additional variable. It's called the modulation index. Now the modulation index describes in very simple terms how strong the modulation is applied to the carrier wave. And it's set like this. Fm is the frequency of our modulating wave, and beta is the value we can change. And this is basically frequency modulation. Now, there's one thing to mention. The function we set for m needs to be the integral of the function we want to set in. For example, if I want to modulate my carrier wave, which is a sine wave, with a sine wave, then the integral would be minus cosine. That's why here we have minus cosine. I've mentioned that the Fourier series is not so efficient when it comes to real-time applications. So why is the trigonometric function so much more efficient? That's because if we calculate all the samples of the trigonometric function, we only need to do this once. And for the Fourier series, we need to calculate the samples at least, for example, in this case, 50 times and add them all together. This is a huge difference. A different problem is how do we do frequency modulation with this kind of formula? Because where do we add our modulating wave? It's much easier on a trigonometric function. Now about frequency modulation. I've mentioned that we need to use the integral of the modulating wave. If we are programming, then calculating the integral works differently, and in my opinion a lot easier. We just calculate all the samples with our equation, for example with our square wave. Once we are finished, we just sum all samples like this. So one sample is the sum of all previous samples. And after that we will need to normalize our samples because the values will now range between 0 and maybe a few thousands. So that's how we can create the integral of a function. And that's also how it works on this program. When I click on calculate integral. Now I will create the integral of the square wave, which is surprisingly the triangle wave. So basically I could also use the integral of the square wave formula as my formula for the triangle wave. The integral of the sawtooth wave looks like this. And the integral of the triangle wave is very similar to a sine wave. And now I choose as my carrier signal a sine wave. And I apply the modulation. Now, because my modulation index is 0, nearly 0, we can't see anything. I will increase it now. And there, that's what we get. Each waveform changes the frequency of the carrier wave in a different way. The triangle wave continuously changes the frequency between two values. The sawtooth wave continuously changes the frequency to a maximum and then drops it to the lowest value. And the square waveform changes between two frequencies instantly without any smooth transition. Now we will change the carrier wave to a triangle wave. and to a sawtooth wave, and to the square wave. And we can also show our modulating wave. Okay, how do we turn this carrier signal, what we see here, into an actual sound? That's pretty easy because we already have done everything what we need. We already have calculated all our samples, and we just simply need to save those samples to a file, to a wave file, for example, which we can play with any music player. This is the code of the application, and we can see here the formulas for the waveforms, and those formulas just return a list of those samples. And to save it to a wave file, for Python there is a library which is called wavefile, and we just need to import it, and then we need to write a single line to save it, and this is the line, and this method here just updates our carrier wave, what we can see here on the bottom, and every time it updates the carrier wave, it also saves all the samples to the wave file with a sample rate of 44,100. The sample rate says how many samples are used to save or to represent a signal in 1 second. When I say I have a sampling rate of 44,100 Hertz, my signal has 44,100 samples in 1 second. And there we have our wave file, and I will just open Audacity and I will drag and drop it. And there is our signal. Now it's normalized between 0 and 1, and we can also normalize it between minus 0.5 and 0.5. And then we can just play it. I've prepared 2 examples which are a bit more complex. They use 3 waveforms, and on the top we have a carrier wave, which is a sawtooth wave with a frequency of 400 Hz, and it's modulated by a triangle wave with 10 Hz and a modulation index of 200, and this second wave is also modulated by a waveform which is a sawtooth wave and has a frequency of 0.5 Hz and a modulation index of 200. And this sounds like this. Now on the bottom we have basically the same example, but here our carrier wave is a square wave. Okay, that's it. I hope you could learn something from this video, and I will see you in the next video.